This paper presents a systematic approach to optimize robot motion for tracking a specified spatial curve with dual robot arms using robot motion primitives. Applications with industrial robots often require an end effector tool to closely track a specified path under certain tracking accuracy, path speed, and path speed uniformity. Industrial robot motion is programmed through waypoints connected by motion primitives, offering high inner control loop rate. For cold spray applications, challenges include redundancy resolution, tracking accuracy as tight as 0.5 mm in position and 3 degrees in the spraying direction, fast traversal speed within 5% speed uniformity. Current practice requires human operators to go through the tedious process of manually tuning the motion parameters, often with less than optimal results. All industrial robots provide 3 types of motion primitives: Move L, linear in Cartesian space; Move C, circular arc in Cartesian space; and Move J, linear in joint space. We decompose the problem into 3 steps: system configuration optimization to solve joint space trajectory, waypoint optimization to populate motion command with primitives, waypoint iteration to improve the tracking performance. In this paper, we focus on 2 representative target curves. Curve 1 is a multi-sinusoidal curve on a parabolic surface. Curve 2 is the leading edge curve of a representative turbine fan blade. The first step is to resolve the redundant degrees of freedom, which includes the relative base pose of the 2 robot arms and the redundant 7 degrees of freedom during relative traversal process. Our redundancy resolution optimization includes local quadratic programming optimization to resolve the relative motion between both robot arms, path speed estimation given joint velocity limit and experimental joint acceleration limit, and global optimization with differential evolution on the traversal speed, relative robot base pose, and the initial robot configuration. We determine the robot joint acceleration limit experimentally on physical robots with different joint configurations, and the results are stored as configuration-dependent lookup table. This video shows the optimized configurations for both curves with dual arm setup. We use ABB Multimove to achieve synchronized motion command for both arms, and then apply the greedy fitting algorithm to search for the combination of motion primitives for both arms to achieve the desired relative trajectory. We improve the tracking performance by adjusting the waypoints locations throughout runs. First, through proportional feedback, followed by multi-peak model-based numerical gradient descent on waypoints around large errors. The overall workflow is packaged within an integrated user interface, allowing users to choose the robot's desired traversal 5DUF curves, traversal speed, and maximum allowed trajectory error. This interface also leverages Tesseract Robotics for in-browser kinematic visualization before execution. This video shows the waypoint adjustment step for the 2 target curves with dual arm setup in Robot Studio simulation on the user interface. With the initial motion program, the worst-case tracking error is way above the requirement. By iteratively updating the waypoints, the tracking error quickly reduces and eventually meets the tracking requirement. Once validated in simulation, we apply our algorithm to the physical robot. Industrial robots can only achieve certain tracking repeatability. For example, ABB IRB 6640 has the tracking repeatability of 1.06 mm. We therefore evaluate the executed trajectory over a 5-run average. We used a laser pointer as the mock spray gun, pointing directly onto the parabolic surface. In this dual arm setup for curve 1, the tool moves at 450 mm per second relative to the parabolic surface. After 4 iterations, the tracking accuracy meets the tracking requirement. This video shows the dual arm trajectory tracking for curve 2 executed at 1400 mm per second as the relative path speed. The error drops as each iteration updates and finally takes 10 iterations to meet the tracking requirement. We are currently working on applying the algorithm to a robot with a motion capture system for direct tool pose measurement. Our algorithm could also be extended to motion with contact, and we're also applying this algorithm onto multi-robot coordinated additive manufacturing. This project is supported by the ARM Institute and developed at Rensselaer Polytechnic Institute.